Worlds Within Worlds, The Story of Nuclear Energy, Volume Number 1. Atomic Ways, Energy, Electricity, by Isaac Asimov, U.S. Energy Research and Development Administration Office of Public Affairs, Washington, D.C. 20545. Library of Congress Catalog Card Number 75-1894-77, 1972. Nothing in the history of mankind has opened our eyes to the possibilities of science as has the development of atomic power. In the last 200 years, people have seen the coming of the steam engine, the steamboat, the railroad locomotive, the automobile, the airplane, radio, motion pictures, television, the machine age in general, yet none of it seemed quite so fantastic, quite so unbelievable as what man has done since 1939 with the atom. There seemed to be almost no limit to what may lie ahead. Inexhaustible energy, new worlds, ever-widening knowledge of the physical universe. Written by Isaac Asimov. Introduction. In a way, nuclear energy has been serving man as long as he has existed. It has served all of life. It has flooded the earth for billions of years. The sun, you see, is a vast nuclear engine, and the warmth and light that the sun radiates is the product of nuclear energy. In order for man to learn to produce and control nuclear energy himself, however, something that did not take place until this century, 3 lines of investigation, atoms, electricity, and energy, had to develop and meet. We will begin with atoms. Atomic weights. So, as long ago as ancient Greek times, there were men who suspected that all matter consisted of tiny particles which were far too small to see. Under ordinary circumstances, they could not be divided into anything smaller, and they were called atoms, from a Greek word meaning indivisible. It was not until 1808, however, that this atomic theory was really put on a firm foundation. In that year, the English chemist John Dalton published a book in which he discussed the atoms in detail. Born in 1766 and died in 1844. Every element he suggested was made up of its own type of atoms. The atoms of one element were different from the atoms of every other element. The chief difference between the various atoms lay in their mass or weight. Also, as a quick footnote, it must be clarified that mass is the correct term, but weight, which is a somewhat different thing, is so commonly used instead that in this book I won't try to make any distinction. Dalton was the first to try to determine what these masses might be. He could not work out the actual masses in ounces or grams, for atoms were far too tiny to weigh with any of his instruments. He could, however, determine the relative weights, that is, how much more massive one kind of atom might be than another. For instance, he found that a quantity of hydrogen gas invariably combined with 8 times its own mass of oxygen gas to form water. He guessed that water consisted of combinations of 1 atom of hydrogen with 1 atom of oxygen. A combination of atoms is called a molecule, from a Greek word meaning a small mass. And so hydrogen and oxygen atoms can be said to combine to form a water molecule. To account for the difference in the masses of the combining gases, Dalton decided that the oxygen atom was 8 times as massive as the hydrogen atom. If he set the mass of the hydrogen atom at just 1, just for convenience, then the mass of the oxygen atom ought to be set at 8. These comparative or relative numbers were said to be atomic weights, so that what Dalton was suggesting was that the atomic weight of hydrogen was 1 and that the atomic weight of oxygen was 8. By noting the quantity of other elements that combine with a fixed mass of oxygen or of hydrogen, Dalton could work out the atomic weights of these elements as well. Dalton's idea was right, but his details were wrong in some cases. For instance, on closer examination, it turned out that the water molecule was composed of 1 oxygen atom and 2 hydrogen atoms. For this reason, the water molecule may be written H2O, where H is the chemical symbol for a hydrogen atom and O for an oxygen atom. It is still a fact that a quantity of hydrogen combines with 8 times its mass of oxygen. So, the simple oxygen atom must be 8 times as massive as the 2 hydrogen atoms taken together. The oxygen atom must therefore be 16 times as massive as a single hydrogen atom. If the atomic weight of hydrogen is 1, then the atomic weight of oxygen is 16. At first, it seemed that the atomic weights of the various elements were whole numbers and that hydrogen was the lightest one. It made particular sense then to consider the atomic weight of hydrogen as 1 because that made all the other atomic weights as small as possible and therefore easy to handle. The Swedish chemist Jöns Jacob Berzelius continued Dalton's work and found that elements did not combine in quite such simple ratios. That is Jöns Jacob Berzelius, J-O umlaut N-S J-A-K-O-B B-E-R-Z E-L-I-U-S Berzelius, born in 1779 and died in 1848. A given quantity of hydrogen actually combined with a little bit less than 8 times its mass of oxygen. Therefore, if the atomic weight of hydrogen were considered to be 1, the atomic weight of oxygen would have to be not 16, but 15.87. As it happens, oxygen combines with more elements and more easily than hydrogen does. The ratio of its atomic weight to that of other elements is also often a whole number. In working out the atomic weight of elements, it was therefore more convenient to set the atomic weight at a whole number than that of hydrogen. Berzelius did this, for instance, in the table of atomic weights he published in 1828. At first, he called the atomic weight of oxygen 100. Then, he decided to make the atomic weights as small as possible, without allowing any atomic weight to be less than 1. For that reason, he set the atomic weight of oxygen at exactly 16, and in that case the atomic weight of hydrogen had to be placed just a trifle higher than 1. The atomic weight of hydrogen became 1.008. This system was retained for nearly a century and a half. Throughout the 19th century, chemists kept on working out atomic weights more and more carefully. By the start of the 20th century, most elements had their atomic weights worked out to 2 decimal places, and sometimes 3. A number of elements had atomic weights that were nearly whole numbers on the oxygen equals 16 standard. The atomic weight of aluminum was just about 27, that of calcium almost 40, that of carbon almost 12, that of gold almost 197, and so on. On the other hand, some elements had atomic weights that were far removed from whole numbers. The atomic weight of chlorine was close to 35.5, that of copper to 63.5, that of iron to 55.8, that of silver to 107.9, and so on. Throughout the 19th century, chemists did not know why so many atomic weights were whole numbers, while others weren't. They simply made their measurements and recorded what they found. For an explanation, they had to wait for a line of investigation into electricity to come into fruition. Electricity. Units of electricity. Through the 18th century, scientists had been fascinated by the properties of electricity. Electricity seemed, at the time, to be a very fine fluid that could extend through ordinary water without taking up any room. Electricity did more than radiate through matter, however. It also produced important changes in matter. In the first years of the 19th century, it was found that a current of electricity could cause different atoms or different groups of atoms to move in opposite directions through a liquid in which they were dissolved. The English scientist Michael Faraday, born in 1791 and died in 1877, noted in 1832 that a given quantity of electricity seemed to liberate the same number of atoms in a variety of different elements. In some cases, though, it liberated just half the expected number of atoms, or even in a few cases, just a third. By the way, this is Michael Faraday. Michael Faraday, M-I-C-H-A-E-L-F-A-R-A-D-A-Y, Michael Faraday. Scientists began to speculate that electricity, like matter, might consist of tiny units. When electricity broke up a molecule, perhaps a unit of electricity, attached itself to each atom. In that case, the same quantity of electricity, containing the same number of units, would liberate the same number of atoms. In the case of some elements, each atom could attach 2 units of electricity to itself, or perhaps even 3. When that happened, a given quantity of electricity would liberate only 1/2, or only 1/3, the usual number of atoms. Thus, 18 units of electricity would liberate 18 atoms if distributed 1 to an atom, only 9 atoms if distributed 2 to an atom, and only 6 atoms if distributed 3 to an atom. It was understood at the time that electricity existed in 2 varieties, which were called positive and negative. It appeared that if an atom attached a positive unit of electricity to itself, it would be pulled in one direction through the solution by the voltage. If it attached a negative unit of electricity to itself, it would be pulled in the other direction. The units of electricity were a great deal more difficult to study than the atomic units of matter, and throughout the 19th century, they remained elusive. In 1891, though, the Irish physicist George Johnstone Stoney, born in 1826 and died in 1911, suggested that the supposed unit of electricity be given a name at last. He called the unit an electron. Cathode rays. An electric current flows through a closed circuit of some conducting material, such as metal wires. It starts at one pole of a battery or of some other electricity generating device and ends at the other. The 2 poles are the positive pole or anode and the negative pole or cathode. If there is a break in the circuit, the current will usually not flow at all. If, however, The brake is not a large one, and the current is under high driving force, which is called the voltage, then the current may leap across the brake. If two ends of a wire making up part of a broken circuit are brought close to each other with nothing but air between, a spark may leap across the narrowing gap before they actually meet, and while it persists, the current will flow despite the break. The light of the spark and the crackling sound it makes are the results of the electric current interacting with molecules of air and heating them. Neither the light nor the sound is the electricity itself. In order to detect the electricity, the current ought to be forced across the gap, containing nothing, not even air. In order to do that, wires would have to be sealed into glass tube from which all or almost all the air was withdrawn. This was not easy to do, and it was not until 1854 that Heinrich Geissler, born in 1814 and died in 1879, a German glassblower and inventor, accomplished this feat. The two wires sealed into a Geissler tube could be attached to the poles of an electric generator, and if enough voltage was built up, the current would leap across the vacuum. Such experiments were first performed by the German physicist Julius Blücher, born in 1801 and died in 1868. In 1858, he noticed that when the current flowed across the vacuum, there was a greenish glow about the wire that was attached to the cathode of the generator. Others studied this glow, and finally the German physicist Eugen Goldstein, born in 1850 and died in 1931, decided that in 1876 that there were rays of some sort beginning at the wire attached to the negativity charged cathode and ending at the part of the tube opposite the cathode. He called them cathode rays. Those cathode rays, it seemed, might well be the electric current itself, freed from the metal wires that usually carried it. If so, determining the nature of the cathode rays might reveal a great deal about the nature of the electric current. Were cathode rays something like light, and were they made up of tiny waves? Or were they a stream of particles possessing mass? There were physicists on each side of the question. By 1885, however, the English physicist William Crookes, born in 1832 and died in 1919, showed that cathode rays could be made to turn a small wheel when they struck that wheel on one side. This seemed to show that the cathode rays possessed mass and were a stream of atom-like particles, rather than a beam of massless light. Furthermore, Crookes showed that the cathode rays could be pushed sideways in the presence of a magnet. This effect, when current flows in a wire, is what makes a motor work. This meant that, unlike either light or ordinary atoms, the cathode rays carried an electric charge. This view of the cathode rays as consisting of a stream of electrically charged particles was confirmed by another English physicist, Joseph John Thomson, born in 1856 and died in 1940. In 1897, he showed that the cathode rays could also be made to take a curved path in the presence of an electrically charged objects. The particles making up the cathode rays were charged with negative electricity, judging from the direction in which they were made to curve by electrically charged objects. Thomson had no hesitation in maintaining that these particles carried the units of electricity that Faraday's work had hinted at. Eventually, Stoney's name for the units of electricity was applied to the particles that carried those units. The cathode rays, in other words, were considered to be made of streams of electrons, and Thomson is usually given credit for having discovered the electron. The extent to which cathode rays curve in the presence of a magnet or electrically charged objects depended on the size of the electric charge on the electrons and on the mass of the electrons. Ordinary atoms could be made to carry an electric charge, and by comparing their behavior with those electrons, some of the properties of electrons could be determined. There were, for instance, good reasons to suppose that the electron carried a charge of the same size as one that a hydrogen atom could be made to carry. The electrons, however, were much easier to pull out of their straight line path than the charged hydrogen atom was. The conclusion drawn from this was that the electron had much less mass than the hydrogen atom. Thomson was able to show, indeed, that the electron was much lighter than the hydrogen atom, which was the lightest of all the atoms. Nowadays we know the relationship quite exactly. We know that it would take 1837.11 electrons to possess the mass of a single hydrogen atom. The electron is therefore a subatomic particle, the first of this sort to be discovered. In 1897, then, two types of mass-containing particles were known. There were the atoms, which made up ordinary matter, and the electrons, which made up electric current.